Welcome to Webinar Wednesday. I'm Kevin Corson, PCI's Executive Director. On behalf of PCI, thank you for joining us for today's webinar, Improving the Stability and Surface Effect of Powder Coating, presented by Muhsin Kanuni and Mike Watson of Clariant. Before we get started, I'd like to remind everyone that all attendees are on mute, so if you have any questions along the way, please type them in the questions panel. The speakers will address the questions at the end of the webinar. If we run out of time, you will have an opportunity to connect with them via email after the webinar. Their contact information will be noted at the end of the presentation. This webinar is being recorded and will be available through the PCI store within 2 business days. All attendees will receive a brief survey after the webinar. Please take a few moments and reply to the survey. We appreciate your feedback as PCI continues to develop new programs to offer the topics and training you need. Now, I'd like to introduce the presenters for today's webinar. We have Dr. Muhsin Kanuni, who is the Marketing Manager for Coatings with Clariant Performance Additives. During his career, he was a Technical Service and Development Manager in resins, served as Global Marketing Manager for Consumer Electronics and Automotive Coatings, and occupied several positions at Ciba Specialty Chemicals with a focus on light and heat stability of coatings and polymers. Muhsin holds several patents and publications on light stabilizer additives and has been an adjunct chemistry professor for over 7 years at City University of New York and Kenshaw State University. We also hear from Muhsin's colleague, Mike Watson, who has been in the additives industry for more than 30 years, serving coatings, adhesives, and plastics applications. He holds a Bachelor of Science in Chemistry from Purdue University. In his current role with Clariant Additives, he is the Technical Segment Manager for their Advanced Surface Solutions in Coatings and Inks with customers in the US and Canada. Thank you both for being here. I will now turn it over to you. Go ahead, Muhsin.
Hello, everyone. Thank you so much for attending today's webinar about improving the stability and the surface effect of powder coatings. Right, so the content of our presentation today, brief introductions about Clariant, but more importantly, we will talk about the heat and light stabilizers with an overview of the stabilization mechanism. So we will go into the details of how powder coatings get degraded and also how we can prevent that. And that will be our section about additives selection criteria. That will also involve the gas fading stabilizations, which is an issue very often faced by powder coatings application, especially for gas ovens. And then I will pass it on to my colleague Mike to go over his advanced surface solutions for powder coatings. So basically, when we talk about light stabilizer and heat stabilizer, what we see is, sorry, I missed my presentation. Yeah, so we have mainly 2 different types of stabilizer. We have the UV absorber, which, as indicated by its name, effect is basically filtering the UV light, and that is, as a consequence, protecting the coatings. Very important about the UV absorber is the Beer-Lembe principles, which pretty much dictate that the absorbance, which is how much light is filtered by the UV absorber, is directly proportional to the thickness of the coatings, to the dosage of the UV absorber, and epsilon, which is the extension coefficients. The extension coefficients is actually based on the molecules, which we will talk on the next couple of slides. But again, more importantly, to know about UV filter is that their performance is directly proportional to the dosage and the thickness of the coatings, which basically means that if you have a coatings of, for instance, 2 mils, and if you are using 2% as an example of a UV absorber, if you are changing this thickness to 1 mil, you will need to multiply your dosage of UV absorber by 2 in order to get the same performance that you were getting at 2% for 2 mils. And obviously, if you are increasing your thickness of the coatings, then you might need to also decrease the thickness of the dosage of the stabilizer, because this is a direct proportional relationship between dosage and thickness of the coatings when it comes to the UV absorber. Also important about the UV absorber is that the dosage would be different if you are formulating a clear system versus a pigmented system. In a clear system, you don't have any component in your coating formulations that will absorb the UV light and will give you some protections about UV filters. However, if you are formulating a pigmented system, then obviously the pigment or the filler will have some effect of UV absorber, and this will allow you to limit your dosage of the UV absorber. That is why our recommended dosage is between 1% and 4%. 1% will be a standard dosage for a pigmented system at about 2 mils film thickness. And then 4% will be also the recommended dosage if you have a clear system and you need quite a good absorbance at 2 mils. So again, the dosage always proportionally related to the thickness. Another factor about UV absorber is the intensity of the UV light and pretty much how they work, and that is what we see in the graph next to it. In regards to the chemistries of the UV absorber, there is actually quite a few used in the coatings system. We have the benzophenone, oxanalenide, benzotriazole, and triazine. If you look carefully at those molecules, you will see that they all have this double bond oxygen close to a hydrogen. And pretty much what this tells us is the way how the UV light is absorbed is by a tautomeri effect, where you will have this transition of this hydrogen from the OH group to the double bond O. However, this tautomeri is not exactly the same in terms of its kinetics, as well as in terms of how it will go back to your ground states, which explain the durability of a UV absorber. So basically the triazine, which is known to have a very good durability, and it's very likely the UVA of choice for high performance requirements, the triazine will very likely last much longer than the benzophenone or oxanalenide, and even some benzotriazoles. While for benzotriazoles, there is actually several chemistries there, and among the benzotriazoles, there is a big differentiation between the photopermanence of the different benzotriazoles. But basically, in the other coatings industry, for high performance applications, we can either seek for a very high photopermanent benzotriazole, meaning a benzotriazole that will have a long-lasting effect in the coatings, or very likely also a triazine. And that is what we see in the small graph on the bottom left, that you see the years of Florida exposure, and just to show you how durable is my different chemistries in regards to durability in a coating matrix. In this case, it's for the Florida exposure. Another important feature of the UV absorber, in addition to the photopermanence, which again is a critical fact in order to select the UV absorber that will give you the best durability for your applications, the other factor which is also critical, it's the absorbance profile of those UV absorbers. As you can see in this graph, a benzotriazole, a triazine, or oxanalenide don't really absorb in the same wavelength. And also, when we compare that absorptions to the natural sunlight, which is the graph in the back, the natural sunlight intensity actually increases as you go from short wavelength, the UVB area, to the visible light, which means the intensity increasing, you will have more photons, for instance, at 375 nanometers that you have at 300 nanometers. However, important to keep in mind, the energy carried by the photon of the natural sunlight is reversely proportional to the wavelength, which means those photons at 310, 320 nanometers will carry a much higher energy and consequently will have a much higher negative effect or a degradation effect on the coatings applications. And that explains why the UVB absorption is critical for UVA, and triazine having the highest one will very much dictate also what happened in a natural weathering test. The benzotriazoles, it's kind of a broader absorbance, as we can see here. This is the yellow graph and the blue graph. They definitely absorb more in the UVA area, but because they are lacking the absorptions that you see of the UVB, of the triazine in the UVB area, that also can explain some of the performance difference between the triazine and the benzotriazole. Now, this is also important to know the absorptions of the UVA when it comes to what type of weathering test you're going to conduct for your experiment. So as you can see in the small graph on the right side, usually we can either do a xenon weatherometer testing for an X-ray weathering. We can do QVA on QVA, which is shown here as UV-Con A, or we can do QVB. They're very different, as you can see by the intensity and by the wavelength of those lamps. But what we can say from this graph is that xenon will probably be the one that will correlate the most to the outdoor weathering, because as we can see, the absorption or the spectra of the xenon lamps is kind of going the same direction as the natural sunlight, starting very low at the 300 nanometers and increasing just like the natural sunlight when we go to the visible light. So xenon will probably be one of the best accelerated weathering tests. However, we also have a lot of usage of a QUVB and a lot in the powder coatings. So while QUVB has a maximum intensity at 330 nanometers, which is very much exaggerating compared to natural sunlight, as we can see here. But this is a test that can give you a much faster result in terms of weathering. Not really, again, representing the natural weathering, but if you have a limitation in timing and you want to get some indication, again, if you want to get some indication of the weathering of your powder coatings, then QUVB could be a method to go, even though there is also some standard that require QUVB. So when it's a standard, you will have to do the QUVB. Then the QVA is a lot less used for accelerated weathering for exterior applications. It is mainly used for accelerated weathering for an indoor applications. So we see it a lot, for instance, in epoxy coatings, for interior applications where QVA is used. But I think it's important to know what type of weathering test you'll be doing, because that will also help you to select the right UV absorber based on your performing test of weathering. Now, in regards to the amine light stabilizer and the antioxidant, those two are the heat stabilizer, if you prefer, even though the amine light stabilizer is mainly here light stabilizers, a synergistic effect with the UVA. So the UVA filter is our number one mechanisms to protect the coatings, and then synergistically with it, we use an amine light stabilizer that pretty much perform using the following the Denisov cycles, and that is actually trapping radicals that are formed during the degradation process of the coatings. Very likely, very similarly to an antioxidant. The main difference is obviously an antioxidant is used as a heat stabilizer, where the amine light stabilizer is primarily used as a light stabilizer. Now, because we don't have anymore the Beer-Lembe principles, There is no correlation anymore between the thickness of the coatings, the dosage of the Hindered amine light stabilizer, and the performance. Also because we are following these Denisov cycles, which pretty much regenerate the nitroxide radicals, which is your active component of a HALS. The dosage of HALS is very often significantly less than that of a UVA. As you can see here, we recommend between 0.25 to 0.5%. So here in light stabilizers, synergistic effect with the UV absorber, not directly related to the thickness to the coatings, the concentration. It does not mean that the more I put in, the better might be my performance. There will be an optimum dosage. And then we have the antioxidant. And in regards to antioxidant, we have actually two types, the primary antioxidant and the secondary antioxidant. So the secondary antioxidant, as you can see here, they are mainly here to stop the degradation process of the hydroperoxide, where the primary antioxidant trap the radicals that are formed by the alkyl and peroxy radicals. In regards to powder coatings, very often we would choose one or the other. When cost is an issue, we will probably focus on a primary antioxidant unless we do a gas oven baking, and then we'll have to change into a secondary one, because the primary antioxidants, such as the 1010, for instance, the phenolic antioxidant, are known to cause strong discoloration in presence of NOx, which is about gas fading. But we'll talk about that later in our presentations. So to summarize, two types of antioxidants, the primary antioxidant, the secondary antioxidants. Why are they needed into my powder coatings formulation? Primarily because you are extruding your powder coatings, or extrusion of the powder coatings is part of the formulation of it. So which means we have a great deal of heat, and we need to protect the coatings from that heat during the oxidation process. But also the baking, it's done at a quite high temperature, and we also need an antioxidant for those two phases, if you want, of heat cycle of a powder coatings. The preparation, the exudations need an antioxidant, and then the baking, which is done at high temperature, will also need an antioxidant. So to summarize, for heat stability, we will use an antioxidant, primary or secondary. For light stability, we will use a Hindered amine light stabilizers, which is a radical scavenger, and we will use a UV absorber as a way to filter the UV light and protect our coating. Yeah, the Denisov cycle is only showing now, but I did explain it earlier. Okay, so now let's look at some performance and see how those UV absorb, in this case, the antioxidant is performing. So among the antioxidant, there's actually quite a lot of choices, and that's why that's what we see here: AO1, AO2, AO3, AO4. So those are different chemistries of antioxidant. Even within the phenolic one, you have quite a choice. However, they don't perform the same, and that's what we see in these evaluations. We have the contribution to the yellowing. So the Y graph here, the Y axis is delta B, which correlates to the yellowing of the coatings. And then we can see the type of coating we have used in this study. It's a white pigmented polyester pyramid system, cured at 200 degrees Celsius. And we use 0.5% of the antioxidant in this experiment. And what do we see is we see that 10 minutes, there is really no much difference between the different antioxidants when it comes to the yellowing. However, when you go to 60 minutes, and very often we call this like an overbaking test, and there is two ways to do an overbaking test, either by increasing the temperature of your oven or by extending the time of the curing. And when we do the overbaking test here, we can see that there is quite a significant difference in the yellowing between the different antioxidants. And antioxidant here, PQ, which is a high efficient phosphorus-based antioxidant, we see that it's really providing us just a slight increase of yellowing compared to the other phenolic antioxidants. So yeah, it's very important when we do our baking that we also check the different chemistries of the antioxidant to ensure we get the best performance. Here is another test where we have done, as I mentioned earlier, we can do the standard baking temperature at 200 degrees Celsius for 30 minutes. And we have two types of overbaking test, the 60 minutes at the same temperature or the 30 minutes at 230 degrees Celsius. And there is definitely here quite a significant difference between the different stabilizer. In this case, we also added the HALS, which is a component that will be used in a powder coatings formulations. And we want to see what is the effect of, for instance, a phenolic antioxidant, a thioether antioxidant, and then phosphorus-based, phosphide-based antioxidant, which is the PQ. And what we see here is, again, at 200 degrees Celsius, which is your standard temperature, 30 minutes, there is really no big differences when it comes to the yellowing of the system. Same here, white pigmented PS primid. However, when we go to 200 degrees Celsius for 1 hour, we see that there is a difference. This is what we saw already in the previous slide. But if you do your overbaking test by increasing the temperature cure of your oven, the delta B, the yellowing, is significantly more while we are staying at 30 minutes of a baking time. And here we see really that there is a significant difference between the phenolic antioxidant, AO5, the thioether, AO5, and then again, the antioxidant PQ, the phosphate-based ones, is giving us a better performance. And we even had, and this is something that is quite interesting when you are a formulator, is you can also play by mixing antioxidant, and that's what we did here. So we mixed AO5 and AO3 because keep in mind that the cost of those are not equivalent, and consequently, by mixing antioxidant to achieve the best performance while maintaining cost at bay, it's also a nice way and a wise way to get what you're looking for in terms of heat stability while also keeping cost moderate. So this slide is just to talk about the gas oven, which is obviously quite popular in the US because gas is in many areas. Gas oven, it will be a lot cheaper than electric oven. But when you have a gas oven, you have the direct gas oven, or you have the indirect gas oven. And in direct gas oven, you are forming NOx that's generated by the flame. And those, as I mentioned earlier, really cause severe yellowing in the presence of a phenolic antioxidant. And in order to overcome this yellowing, the AOPQ, the one we talked about earlier, have really a good performance to prevent this yellowing. But there is also some HALS, and that is also quite interesting, that some hindered amine-like stabilizers can also be used as a gas fading stabilizer. And that's what we will see. So again, when there is no NOx formed, or it's what we call an indirect gas oven, any antioxidant can be used, and obviously it will make more sense to go to a phenolic stable antioxidant because of the cost advantage of such stabilizer. So here we see the performance in NOx, and just to confirm what we mentioned earlier, that when we are using a phenolic antioxidant, actually our yellowing, in this case 30 minutes, and the NOx is really even worse than a no additive stabilizations. And we see that the AO3, it's not much better, but really the AO4, which is our phosphite-based antioxidant, really significantly reducing the yellowing or the discoloration, which is caused by NOx in a direct gas oven formulation. So when it comes to the HALS, as I mentioned earlier, HALS is a little bit more tricky if you want to use it into a powder coatings application, and especially for gas fading applications. And when we compare the standard HALS and when we compare to what we call here HALS PY, but just to say that this HALS is actually designed, so the HALS that you want to use has to be designed for high temperature use. And in this case, nothing better than a polymeric HALS, because when you have a polymeric HALS, you have this high molecular weight, and we know consequently that this will have an impact on the TGA. And that's what we see here. The other factor to keep in mind when we talk about a polymeric HALS for powder coatings, the HALS has to be soluble once you heat your systems and once you form your coatings, especially if it's a clear, your HALS has to be soluble. So this is another factor to keep in mind when we talk about the polymeric additives into a powder coatings formulations. And this HALS actually was designed to be soluble. And that means not only, as we can see here, we only get 10% loss at 350 C, which is pretty much based on the TG, versus 50% loss for a low molecular weight HALS. So no migration, also this is something you can expect from a polymeric HALS, low volatility. The advantage also of having a polymeric HALS is on the labeling. This type of HALS actually is label free, which means that when we look at the SDS and if you compare it to a standard HALS used in powder coatings applications, what you will find is product not labeled at all. And that's really quite an advantage when you have an additives that allows you to formulate a powder coatings without any toxicological profile, and that will enhance not only the performance, because again, polymeric HALS will last longer, there will be less loss during the curing of the coatings, but also providing you the advantage of the labeling. Here again, the volatility, when we compare those HALS, percent volatility at a different temperature and time, and we really see that the temperature and the isothermic reactions is favorizing significantly, and that makes a lot of sense. Again, being polymeric, you have this high molecular weight. You cannot just come out of the coatings as easily as if you are a standard molecule. So really superior, as you can see here, superior thermal stability, and really highly recommended for high temperature cure powder coatings. I am almost at 11:27, 3 minutes ahead of time. So I will pass it on now to my colleague, Mike Watson, to overview with you the waxes for powder coatings applications.
Thank you, Massine. Thank you, everybody, for joining us today. Some of you already may be familiar with us. We may have met you in the past, but for those of you who are not familiar with us, I wanted to just show you a brief overview of the variety of waxes that we do have. This is our product line that we call Advanced Surface Solutions, basically a fancy name for waxes, but it's because for coatings and inks applications, we're modifying surface properties with these types of waxes. So the ones you see on the screen here are the base waxes that we manufacture, blend, modify, and so forth. And then the micronized waxes is really what's the most common product that we would use in coatings and inks. And these are going to be, micronized to specific particle size, D50 ranges. And that's where we're typically using the micronized type of wax in coatings and inks. I will say in powder coatings, because you're already going to go through an extrusion step in many cases, you can use the base waxes, which come in flakes or granules or coarse powders. So some powder coatings customers will use the base waxes because you're going to be running it through your extruder and your grinder anyway. But if you want to add the waxes post-add, which gives you a little more flexibility, you can of course use the Ceradust grades. I'm sorry, not supposed to use that name. The micronized grades. Sorry about that. So for powder coatings, we actually would use both types. But the micronized waxes are going to be those same variety of waxes that I showed on the previous slide: polypropylenes, polyethylenes, modified and unmodified waxes. Typically, the D50 is going to be more 5 to 15. We do have a few that are on the larger end, especially for texturing and powder coatings. But the key here is that it's not only the chemical nature and the chemical structure, but also the particle size distribution that are really going to play a decisive role in the performance in coatings and inks. Today, with powder coatings, I wanted to focus on the PTFE topic, where we've done a lot of recent work in both becoming regulatory compliant, which there's a lot of information on this slide. You may or may not be familiar with it. I'll summarize it here in a bit. But I also just wanted to mention that in the interest of time, I'm focusing on this PTFE topic, whereas also in powder coating, some of our waxes would be suitable for things like adhesion promotion, degassing, low temperature cure applications like MDF, things like that, pigment dispersion, so you get better usage out of your color. So the waxes that we do have for powder coatings can really provide a lot of different benefits, but today I want to focus on this PTFE topic. So you may or may not be familiar with this already, the REACH legislation that is going to ban PFOA levels above 25 parts per billion. It was supposed to take effect in mid-2020. It's been extended to 2022. We're a global company. I'm sure many of you are as well. This regulation wasn't going to specifically apply to the U.S. We're not one of the countries that have signed on to this, but nevertheless, it's affecting our business. It's affecting a lot of people's business because of the global nature of the market. So we were already acting as if this ban was in effect anyway, even though it has been extended for a few years. But at some point, the ban is going to take place. And what it is, for any PTFE applications, whether it's the manufacture, the use, the sale, you have to be below 25 parts per billion PFOA, which is not easy to measure. We have a test that we're confident we can detect down to 2 parts per billion. So we're confident that all of our product line, all of our existing product line is compliant with this regulation. We have documentation to state that, but we are also moving towards PTFE replacement for companies that just want to not even have to worry about the regulation and eliminate the use of these chemicals entirely. So that's what I'm going to talk about today, and that's kind of where some of our newer development has been going lately. So first of all, there's a couple of waxes that we have that are REACH compliant. They still do have the PTFE in there, but they're REACH compliant. A couple different versions. This is just showing some a photo and then some notes about some of the things that it's doing for you. But at a 1% level, these two different ones will provide some textured finish. So you basically got REACH compliant waxes here, polyethylene PTFE blends that can provide you structuring in addition to matting and dirt repellents and anti-slip and all the other sort of surface properties that that waxes provide. But in powder coatings, more so than other coatings and inks applications that we deal with, the structure is sometimes what people are looking for as well. That sort of pebbled structure, and if you want to modify that with your pigment loading and your wax loading, you can really play around with that and get the appearance that you want. So just this slide shows a couple of the newer waxes that are REACH compliant for structuring purposes, and again also giving you some of the other benefits as well. This different slide with the same kind of waxes here, just showing some different photos. And again, 1% dosage is pretty low. We can help you with that. In our own applications lab, we can work with you to sort of hone in on what that optimum level is. You don't want to have to use more than you need, but you want to use enough to get the properties you're looking for. So we can work with you on that. But 1% dosage level here of these two waxes that I'm talking about, again, it's going to provide a matte finish because that particulate at the surface is going to scatter light. So there's always going to be some effect on the gloss or matte appearance. And then, anti-scratch, anti-slip, of course, REACH compliant, and you've got the ability to play around and control the texture appearance of your coatings. So I also want to talk about another wax that we have. Now we're talking about basically PTFE, PFAS free. So this wax has no PTFE at all, so you don't have to worry about that parts per billion. It's obviously REACH compliant because it's not even using the polyfluorochemicals anyway. Here the dosage is a little bit higher, but you can see somewhat in the photo the difference between using 4% of the modified polyethylene, which we would call PTFE free wax, versus a traditional PTFE. For that structuring effect, it's adjustable, so you can adjust the loss in the structure. I'll talk here a bit about flow properties and edge covering, some of the other benefits it provides. And of course, it depends on your system and everything. I mean, a lot of times with the waxes, it is a little bit of trial and error, but that's really what our applications lab is for. So we can definitely work with you on that. And actually, this wax itself is a non-micronized wax, so it would be incorporated, you know, pre-grind, pre-extrusion, and then you'd get the particle size that you need after the fact. But of course, I did mention earlier, but kind of stands to reason that the micronized grades are going to typically be more costly just because it's an extra step. So if you don't have to use micronized grades, you're probably better off using a base grade that's a coarse powder. Here's a couple other photos here of the same wax that I was just mentioning. Now with this wax itself, it has to be used with TiO2 to get that structuring, and you can kind of play around with the dosage of the wax and also the dosage of the TiO2. We are working on developing waxes along this type here, PTFE free for structuring and powder coatings, where you can where you don't have to use TiO2. You can also use carbon black or other pigments as well. But this one we're talking about here, it really does require the TiO2 to get the best structuring benefits. A couple slides ago, I mentioned edge covering, flow properties. So this wax, now we do have a spray booth. We're not spraying complicated parts, three-dimensional parts, furniture, or anything like that. We're basically just spraying flat panels, but yet we're still observing how the edges will flow and how the edge will get coated and covered. And also we've seen commercial experience that's sort of proven that this wax is pretty good when it comes to edge covering and flow, because it just modifies the flow properties to where you get better edge covering. So like it says here, avoiding bead formation and edge shrinkage. So in addition to being, you know, PTFE free and not having to worry about that regulation, you get obviously some other benefits as well. Here is some microscopic, if you really want to get down to what the structuring effect is doing. So on the left is a 2% dosage of the first wax I introduced that is REACH compliant, regulatory compliant, but still is a blend of PTFE and polyethylene. And then on the right is a 4% dosage of the one that we just reviewed, that is the PTFE free wax. So, you know, to the extent that you're really trying to get down to not only what does the structure look like to the naked eye, but really what's the structure doing underneath, this kind of shows you the difference between a fibrous and a bead forming structure effect. So that's really where that visual appearance is coming from. And as usual, I always tend to go faster than we've seen, but again, like I said, you know, I for this purposes of this presentation, I wanted to focus on the PTFE topic. That isn't the only area that we play in powder coatings, but it is what I want to discuss today. So I guess that's the end of our presentation, and we can go through questions if there are any.
All right. Just wanted to remind everybody, if you do have any questions, please type them into the question box, and we would be happy to review with them. Do have a couple questions right now in here, so I'll read them out, and Lucine or whoever wants to answer, decide to hop in here. First question is from Rudy. Do UV absorbers affect chemical resistance or performance properties of powder coatings, such as TGIC, HAA, or polyurethanes?
Yeah, thank you. That's a very good question, because when we talk about a UV absorber, and I will say here, let's extend it to light stabilizers, because again, the UV absorber and the Amine stabilizer works together as a synergistically to stabilize the coatings. So what I was saying is, when we talk about light stabilizers, very often we look at the loss of gloss, we look at the color change, and we don't really realize that actually when you have a degradation of your polymer matrix, which is your coatings, you are also affecting scratch resistance, mechanical resistance, chemical resistance, because as your coatings get weaker, because it's being degraded by the UV light, the heat, the oxygen, the water, so all of those working together as a factor of degradations, that you are not only impacting, as I said, the gloss and the color change, which those are easy to measure, but you definitely also impacting all of the other properties of the coatings.
Okay. The next question from Kim is in reference to slide number 8. So if you could slide back to that slide real quick. What she'd like to know is the temperatures listed in the cure time of the powder.
I don't know how to go back other than one at a time here.
You could just go ahead and just cursor up real quick, or page up.
Yeah, sorry about that. Yeah. Slide 8.
Yes, please.
Yeah, so the temperature that we see here is the temperature of the oven where the curing is taking place. So usually when we do overbaking, which is a very common practice in the powder coating industry, either you extend the curing time 30 minutes to 60 minutes, or you increase the temperature of the oven, which is in this case 230 C, but you keep your curing time the same, which is here 30 minutes.
Okay. Then Kevin has a question for you, different Kevin that is. What is the regulatory status of the benzoyl triazole UVAs?
Oh, this is an excellent question. I've been working on it quite a lot myself in recent months and also last year, because of the regulation of benzotriazole that started with what is known as UV328 and then moving to UV326 from a REACH registration, having the product put as also a substance of very high concern. There is definitely a trend, but I would say more than a trend, there is actually action taken by the Stockholm Conventions to really ban some of those benzotriazoles. And I didn't mention it, but it is one of the reasons why Clariant is investing heavily in a new type of UV absorber other than benzotriazole and triazenes. And yeah, it's an important innovation project for Clariant to be able to come up for the industry with an alternative.
All right, thank you. One more question I have here is, do medium wave IR ovens combined with gas convection create any problems with the UV additives?
Not with the UV additives. The UV additives usually are not really impacted, but by the IR oven slash UV convention ovens. Just things to keep in mind, and I think that it's an important remark here is, as I mentioned earlier, for the HALS and for the UV absorber, their thermal stability and their ability to remain in the coatings is not the same. Yeah, that was too fast. Okay, that was one of the slides that shows depending upon the molecular weight and the chemistry of your UV absorber, you want to make sure that you use one that remain in your coatings. So some of the triazines really will have a good stability in a heat stage of the baking process, meaning that they will stay in the coating. The benzotriazoles, there is a very broad range. Some of them are better than others, and I think that's an important factor here because eventually you will see that in the performance, right? And same for the antioxidant and the HALS. So yeah, you want to make sure that you select a benzotriazole or triazine or HALS that really have tendency to remain in your coatings, and you can see this with the TGA data that I showed earlier. Yeah.
Okay. What about the adhesion on coatings that have silicone when used in PTFE-free waxes?
That's a question.
Yeah, so I didn't show anything, but we do have a wax. It's a polypropylene wax, so it's certainly PTFE free that shows very good adhesion where silicones or sealants are applied on top of the powder coating surface. So I didn't show that, but if somebody's interested, they can follow up with me later. It's a polypropylene wax, so it's obviously PTFE free, and we've got some data on adhesion with sealants.
Okay. All right. That was the last of the questions that I have in right now. So at this point, just want a few reminders here. I want to first thank you, Musin and Mike, and thank everyone for attending this webinar. Just a couple reminders here. Watch for the link to the survey. Take a few moments and give us your feedback. It's important to us. Also, check out the complete technical conference for Powder Coating Week. I've got that on the screen right now. It'll be in Orlando from July 13th to the 16th, and a lot of good technical papers going on there. Registration is open at conference.powdercoating.org. Also, if anyone has some questions after this, I have my email address up there, kevin@powdercoating.org. Feel free to send me an email. I will pass it along to Musin and Mike, and we will get back an answer to you. Other than that, I want to wish everybody and mention just to have a great rest of your day. Thank you.
Thank you.
Thank you.